is there. That Birmingham has more canals than Venice.
Yeah. Well, thank you very much for inviting me to such an interesting meeting, which I've really been enjoying. So I've known Martin since he was doing his PhD at Imperial. So I think that means I've known him for pretty much as long as anybody else here. Yeah, there was Paul, there was Christopher, and Achim, perhaps. But actually, it seems our interaction went back even further because Martin tells me he learnt his love of programming from the ZX Spectrum when he was in Brazil. So I can probably claim to have been, in some sense, been the longest known with Martin. I haven't got a photo of me and Martin and Alex, and if you want to take a photo, we're all here, so you can do it. But the thing, having mentioned the programming, the one thing that really stands out to me from Martin's career is his love of programming. And it's to Martin's credit, he quickly realized that BASIC was not the language that he wanted to use for the mathematics he was doing, but he was doing exact real number arithmetic in Miranda, I suppose, in those days, or Haskell for his PhD. And I very vividly remember on a flight together to a conference in Barbados when he showed me his exhaustive search of an infinite space. And just a short piece of code, well, Ulrich was explaining it yesterday, but I didn't understand it then. I still didn't understand it. It was the most economical program, and it just delivered these magical results. So I think that's one of the most important things that distinguishes Martin's work, his love of programming. But actually what I'm going to talk about is the interaction with Alex that was on the interval objects. So Martin introduced these to me, must have been about 2007, 17. And asked me, can you do it point free? He and Alex hadn't done it point free. So I'll just summarize what they did. And there's one aspect that was in their paper, but not really mentioned much by Alex in his talk just now. And that is the iterativity condition, which is, I'm going to come down to that at the bottom of this slide, but let's explain roughly what's going on. If you've got, you want to characterize the closed interval, and it's useful to consider it as going from -1 to +1 in this setting. So you want to define maps from the unit interval to other spaces, and the paradigm for this, the example you should be thinking of, is if you've got a space which is Euclidean r to the nth, and you've got 2 points of that Euclidean space, then you're trying to characterize the maps that in this setting are going to come out as the affine maps, straight lines from one of the points to the other. So, but what we want to do is characterize this part of the real line without actually referring to the real line. We want to do it in a more general setting. So what we say is that there's some structure that exists on the interval that also exists on those Euclidean spaces that enables us to say, whenever we got 2 points of A, then that enables us to determine a certain kind of map from the real line to the bigger space. And it's really capturing the convex hull. So the structure that's needed on A and I that I'm going to focus on, which is slightly different from the super midpoint algebra structure that Alex was talking about, is, well, first of all, it is a midpoint algebra. You know, you've got midpoints of any 2 points of I or 2 points of A. that are playing the role of x plus y divided by 2. And obviously, you know, if it's going to be anything like these affine convex closure maps, then we want it to preserve the midpoints. But the other thing is, which is a bit more mysterious, and it's still mysterious to me how the two of them came up with it, is this idea of iterativity. So let's talk about iterativity of a space, of a midpoint algebra A. The condition says that for any x we have with an endomap, which I'll call T, think of that as like a tail, I'll see why in a minute, and some map from X to A, which I'll call H, there is a unique map M from X to A that makes this commutative square commute, that makes this square commute. So what the square is doing is from X, first of all, we can take H and T and get something in A cross X. Then we can apply the M to the X part of it. So we go to A cross A, and then take the midpoint and come back down to A. So the iterativity condition, it says that for all diagrams like this, there is a unique M to make this commute. And the theorem that they proved in various settings is various categories, is that I, the real interval, is a free iterative midpoint algebra on 2 elements. So that's what that's doing is talking about these affine maps to a convex hull, but without having to rely on the infrastructure of Euclidean space. Okay, so they were proving this for objects in toposes of various kinds, Dedekind reals, Cauchy reals. I'm not saying that they proved it's true for all these, but they characterized the situations where it works. Okay, now Martin said to me, does this work point free? Does it work for locales? So I started thinking about it, and I proved it does. So that was my paper of 2017. So I'll just have, since this is a types, and I'll just say something about the point freeness. Since this is a workshop on types and topology, I ought to say just a little bit about the meaning of the word "and" here. So one approach for linking the two, and you've seen this cropping up in some of the talks already, is that if you got your type theory, you want to say, how can you find topology within that type theory? And there are various approaches to this, like you can, in a synthetic topology, you might find a particular type theory where everything is topological. Martin has got quite a good track record in finding the implicit topology just in the bare type theory, for instance, with one-point compactifications and Cantor spaces. And in fact, that's what the exhaustive search does, I think. It's getting the implicit topology in the compact Cantor space. Is that a fair way to put it? Yeah. Now, by contrast, you might also look for a type theory in topology. So in topology, you've got a notion of bundles, and a bundle kind of says, given the base points, you've got a space which is the fiber on top of it. So that's a bit like a dependent type theory. And in fact, when you talk about tangent bundles, you're just thinking of it as a dependent space. But just in classical point set topology, there's no way you can make a systematic sense of this. So the question is, well, is there still some way of capturing that dependent type theory just in the pure topology? And you can make it work, but you have to take 2 decisive steps. Otherwise, there's nothing there. So one is you have to work point free. So you have to work with, when I say point free, I include generalized point free spaces that are toposes, but also ungeneralized point free spaces, which are locales. And you need an ultra minimalist foundation like geometric constructions or arithmetic constructions. So you've got no pi types. So you can't just take your established type theories and hope it's going to work. It won't. You have to make a new type theory for it. But by that, for various reasons that I'm not going to go into, you actually gain access to the points. And you don't have to worry about the fact that it's nominally point free. You can still talk about the points. And Ming and I have been starting to work on point free real analysis. And this talk is about pushing that a bit further. So lots of you know about locales. So if you look at what I'm going to do and say, that doesn't look like locales at all, be thankful. If we can do locale theory that doesn't look like locale theory, that's good, right? And that's what I'm going to do. So here's the Escardó-Simpson theorem for I as a point-free space or as a locale. And you know, these really are localic results, even if they don't look it. So the first thing is I is iterative. And so what I do, I mean, I didn't quite do it this way in the paper, but I think it works better this way, is I use the upper hyperspace, the power locale. So that's a space whose points are compact subspaces, sublocales of I. And then because I itself is compact, it appears as a point of the hyperspace. And in fact, it's the bottom point because there's a reversal of order of these things. Okay, so the midpoint map from I squared to I can be extended to one where the second parameter is a compact subspace. So what we're doing, here's the compact subspace, here's another point. You want the midpoint of this one with everything in there, where you just kind of do it point-wise, actually, and you get another compact subspace that's halfway in between. And what's more, as well as being halfway in between, it's smaller. It's got a smaller radius. You can define radius of these compact spaces. So this map M primed with one of the parameters is compact subspace. You can do that, and I'm going to plug that into the right-hand side of the iterativity diagram that I showed you a couple of slides ago. So here's the M primed. The rest of it is unchanged, actually. We've constructed the rest of this diagram in exactly the same way. So what goes on here is we haven't got commutativity yet, but if we've got any F down here, we can do this composite round the top, and we get another thing, which let me call T of F, another map into the hyperspace. So what we do is we take a fixed point of that, right? So that's how we're going to get the commutativity. So this is just domain theory for those of you old enough and with long enough memories to remember domain theory. You start off with the bottom point, bottom map that goes from X, takes everything to I as a subspace of itself. You apply T over and over again, and you must be going bigger as you do that. And you've got a directed join of that, which is that's just a fact about point-free topology. You can make these directed joins. And what's more, the radii of these things, you start off with the radius of I itself is 1. Each time you apply T, you halve the radius and you get bigger and bigger and bigger. So in the limit, it must have 0 radius. So that's a single point. So that tells you how the M factors. It's not just a map into the hyperspace, it factors through I itself. So that's actually what we wanted. So that's proving that I is iterative. And another question that's important is that if we have an arbitrary iterative A, we can do something clever with Cantor space. And I'm thinking of Cantor space as two elements, a stream of signs, a stream of pluses and minuses. Okay, so if we have an iterative A that's equipped with 2 points, so this is a map from 2 to A, got A minus and A plus, then we can play this trick with iterativity. What was X before is now Cantor space, 2 to the omega. Our T map is just the tail on streams. The H map is where we take the head, and then we apply RA. So from a stream, take the heads and we get one of 2 points of A. And then we can apply these. We get a unique midpoint algebra homomorphism from Cantor space. Sorry, it's not a midpoint algebra homomorphism. Get a unique map from Cantor space to A that makes this diagram commute. And in the affine, in the Euclidean case, we can see quite clearly what this map has to do. It takes a stream S, stream of sines, and then you add together sums of negative powers of 2 for where the sign is negative, and sum of negative powers of 2 for where the sum is positive. And take that convex combination of A minus and A plus, and that's the answer. You can see it's a convex combination. The sum of these two is just the sum half plus a quarter plus an eighth plus, and that's just 1, okay? So that's easy. And you can do the same thing with I, with plus and minus 1, and you get a map C from Cantor space to I. C of a stream S is just the sum of these SIs are pluses and minuses, so it's just the sum of that power series. Okay, now here's an interesting thing, and this is something that happens when you're working geometrically point-free, but isn't going to work, or I mean, I'd be interested if people can tell me how to make it work. This is a surjection. Point-free, it's a surjection. That's not saying for every Dedekind real, we can extract a stream out of it. We can't. It's not some constructive magic. We have to do everything continuously, and there's no continuous way to do that. But it does express a conservativity property, which says in some situations you can reason as if a point down here has a stream leading to it. And once you've done it for those, then that actually is enough. So using this idea, it's a proper surjection, in fact, which is clear because these are both compact Hausdorff. So using this, we can express this map as a co-equalizer. And then using that, we can factor through our M, A plus or minus, we can factor it through C, and that gives us our map, instead of from Cantor space to A, it gives us a map from I to A, and then show that's the unique midpoint homomorphism that we're looking for, and then that proves the theorem. Okay, so that's how I proved that result point-free. Now, here's the application. Suppose you come to trigonometry. You want to do trigonometry. Ming and I have done exponential and logarithms. Next thing is, well, how are we going to do trigonometry? So this is about measuring angles, which seems obvious that you can measure angles, but it's perhaps not so clear how to do it. And what you're really looking for is a group homomorphism from the reals to the circle. So if you think of the circle as being embedded in a complex plane, then you're really going for the map cos plus I sine. It's just cos in one component, sine in another component. Now, there's a well-trodden path in constructive mathematics that says you can do that using power series. So this is how it's done in Bishop and Bridges, for instance. You can write down power series for cos and sine, and then you can prove it has the properties that you want. Now so is this what we do? Here's a bit of real line, right? here in cross-section, I hope you can all see it, is a circle. So any child knows you can wrap the real line round the circle, and that is really giving us our homomorphism from R to the circle. And there are no power series in there. I haven't calculated any infinite series, and in fact, it'd be quite difficult if I wanted to find sine and cos of a large number. But the fact that it's such an obvious thing to be able to do suggests that maybe there's an easier way. And I'm proposing this as using the midpoint algebras and interval objects as an easier way. So what the essential idea is, you want midpoint homomorphisms from I to the circle. Now that doesn't quite work. The circle isn't a midpoint algebra, obviously, but if you exclude one point of the circle, if you exclude -1 in the complex plane, then it is a midpoint algebra. And you can calculate this using square roots of real numbers. So what you're looking for is a square root in the complex plane. As we know, it has 2. But if your z that you're trying to find the square root of is not equal to -1, then exactly one of those square roots has a positive real part, and this is what it is. So you see how that works? If here's -1 for you, isn't it, right? So you got I and minus I. -1, the square roots are plus I and minus I. So they both have real part 0. Any other complex number, sort of around here, it's got 2 square roots. One of them has positive real part and the other one has negative real part. So just exclude -1 and you're done. So, sorry?
Positive and negative imaginary.
No, positive and negative real part. One of them has positive real part. Here are the 2 square roots. There's the real part. That's the bit we want positive. We could have taken the negative square root. So using that, we can define the midpoint of Z1 and Z2 as being, you take the square roots of both of them and then multiply them together. So it's really the geometric mean. Okay. Yeah.
I think Paul has a point, but it's not a crucial one. Yeah.
I'm standing by this bit. Exactly one of them has positive real part. Okay, so that's the midpoint algebra structure. So the next question is the iterativity. So that's not so obvious.
Yeah.
Do you agree?
Yeah.
Yeah, okay. So for iterativity, we want to work with closed arcs in a circle, excluding -1. And the reason we go for closed arcs is because the iterativity proof that I had used compactness. So we can scale, we can translate. So really, we might as well choose one closed arc is as good as another. So let's have a look at this one that just goes from, here's the square root of -I, and here's the square root of +I. And we want to show that this closed arc is iterative. Now, okay, okay. So basically, we need a homomorph. We've got a homeomorphism with the closed interval. It's not a midpoint homomorphism. So what we do is use the fact that it's almost a midpoint homomorphism. This is almost a metric space. And now we can use the same proof as before, but instead of it contracting things by a factor of half each time, we can use a factor of kappa, which is about 0.77. And so the radii still decrease, so you still get the iterativity for the same reason. So, so once we've done this, we can get trigonometry. We've got midpoint homomorphisms from I to the part of the circle. The midpoint homomorphisms, they're group homomorphisms as far as the products and sums exist. We can extend the domain, adjust for other angular measures, and we can define homomorphisms from the whole of R to the circle. Just briefly, I'll say something about calculus. We can define arcsine without using sine and cos. Once we know, which we do, that we can integrate in this point-free topology. And using that inverse, we can first of all get inverses for the sine and cos functions, and we can use fundamental calculus, theorem of calculus, to get derivatives of sine and cos. So that's basically that finishes it. So concluding thoughts is, I mean, this is a constructive account. It's closer to intuitions than power series, at least as far as wrapping the strings around goes. We get a whole R-index family of homomorphisms from R to, depending on your angular measure. So are these all the homomorphisms? So there's a question of Pontryagin duality sitting in there and Fourier transforms, but that's just further work, much further work. And there's a final one, which the midpoint homomorphisms are a bit like geodesics, because can we get a curved version of midpoint algebras? Because one of the axioms there is a flatness condition. Can we get curved versions and use these use the interval object properties for giving a sensible account of geodesics? And that's the end. And thank you for having me.
Okay, yeah, before we go to lunch, I think Martin's going to say one thing real quick.
No, just I don't have a question, but I want to say something. So you were mentioning early times at Imperial and the ZX spectrum book. So before going to Imperial, I read both the ZX spectrum book and topology via logic. But it was only when I arrived at Imperial that I realized that they were written by the same person, Steve. And so I found this more surprising than the books themselves. Thank you.
Well, thank you. Yeah.
Very quickly, very quickly.
Okay, so you had the recursion property co-algebras there, but they're probably well-founded co-algebras. But you also had more traditional domain-theoretic fixed points and convergence of series in the reals. I wonder whether you could fold the domain theory and the traditional convergence into some more slightly more complicated well-founded co-algebra.
Can't make it more complicated.
No, I mean to use one technology rather than the mixture of two of them.
I don't know.
Suggestion.
All right, same rules for lunch from yesterday. You can find lunch spots on the website, hopefully, or find a local to help you out. And I believe the next talk is at 1:30. So sorry we're a little bit late, but it's online. So.
Wait, I have a question. Is the speaker still there?
Send an email to Steve, please. I'm sorry.
Remind me advertising John's book.